So far we've covered 2 of Newton's laws. Today we're going to cover the third, and then we're going to talk a little bit about momentum. Okay? So, Newton's third law is when an object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. Another way of saying that is every action has an equal and opposite reaction. Because of this law, we know that forces must always come in pairs. There's an action force. That's the force that the first object exerts on the second one. So, for example, if you push against a wall, that would be the action force. Then your reaction force is going to be whatever that second object exerts back on the first. For example, the wall pushing back on you. Now, if I push on the wall, it's not always easy to tell that there's a reaction force pushing back on me, right? However, if I pushed on this wall and I was wearing roller skates, what would likely happen to me? I'd go backwards. I might fall over. I don't have great balance on roller skates, that's fair. But I would probably roll backwards, right? So a lot of people take that to mean, well, I moved backwards because of the force that I exerted. That's not necessarily true, though, because when I pushed on the wall, which direction was my force going? Towards the wall. Whereas, which direction did I move? Backwards, away from the wall. So we know from our study of forces so far that objects move in the direction of the force acting on them. So if my force was what caused me to move backwards, then my force should have been pushed backwards, not towards the wall. So Newton's third law tells us that my push force is the action force, and then the reaction force of the wall pushing on me is the reason that I move backwards. Forces are equal but opposite. So you might be asking yourself, if these forces are equal in magnitude but opposite in direction, why don't they cancel out and become balanced forces, right? When we had 2 equal but opposite forces acting on our objects in the previous lessons, then they were always balanced. So what's the deal with that? Well, these forces would be balanced except for one minor detail, which is that they are not happening to the same object. If both of the forces in this pair were acting on the same object, they would balance, then the net force would be 0 and the object wouldn't move. However, they are happening to separate objects. Your force, the action force, is pushing on the wall, and the reaction force, which is equal and opposite, is pushing on you. So because they are pushing on 2 different objects, we have motion happen and they are not balanced. Let's look at some examples of action and reaction pairs. We have, in this image, a swimmer in the water. So they are exerting a force on the water with their arm. They're going to pull backwards on it. Well, they're going to pull their arm backwards, but they will push on the water in the backwards direction. Okay? That would be the action force. So if you want to label that with an A on the diagram, you can. Then the water is going to push back on them with an equal force, but in the opposite direction. And if the reaction force is greater than the force of fluid friction, then the net force will be forward and the person will move through the water. However, we've all probably been in water where moving your arm around, you were not creating enough of a force to move you forward, and that's because the action force that you pushed with was not greater than the force of static friction, so the reaction force was not greater, and as a result you didn't move. But as long as you push with enough force, then you should move because that reaction force should overcome that fluid friction. If we want to label these, we could say that this backward force is the action force, and then the forward force from the water would be our reaction force.
Do we have to label it on the test?
Another example, here we have this person jumping rope. So their action force is to push down on the ground. Then the ground pushes up on them. That's the reaction force. And if you push on the ground hard enough, then the reaction force will be greater than the force of gravity on you and you will move upward. Because you can't sustain that force once you move off the ground, you will obviously come back down once you slow down and gravity, which is constantly affecting you, pulls you back to the surface. Okay? But if you don't push with enough force on the ground, then you're not going to leave the ground. My little nephew is discovering this. He's brand new at jumping, and he will stand there and bend his knees, and then he will just simply straighten his knees, and he doesn't leave the ground because he's not yet capable of putting enough force into the ground to lift him off the ground. So your action force has to be great enough that the reaction, which is equal and opposite, is enough to overcome the force of gravity. Otherwise, you're not going to move. Oh, and if we wanted to label, we would simply put the downward force as the action and the upward force as the reaction here. Our final example is the one that I think is the coolest. It has to do with rocket ships. When you burn rocket fuel, it produces these hot gases, and the engine pushes on those gases and pushes them out the back of the rocket. And then those gases push backwards on the engine with equal but opposite force. And because the engine is attached to the rocket, they are also pushing on the rocket because it's all one thing, one piece. If the force of the gas pushing on the engine becomes greater than the force of gravity, then the rocket flies upwards. A lot of people have this mental image in their brain of the rocket leaves the ground because the gases that explode out of the bottom of it push on the ground and push the rocket. But then how does the rocket continue to fly when the rocket is in the middle of the air and there's no ground to push on? Or in outer space where there's no matter at all for it to push on? It happens because of action and reaction forces. In reality, the rocket is flying because the engine pushes on the gas and the gas pushes back on the engine, and those opposing forces cause the rocket to move. Now that we understand the action-reaction forces, let's talk about momentum. Momentum is a measure of how hard it is to stop a moving object, and it's a useful way to describe changes in motion due to action or reaction forces. The equation is that momentum, which we measure with a unit of kilograms times meters per second, is equal to the mass of an object, which we measure in kilograms, times the velocity of an object, which we measure in meters per second. It can be written as P equals M times V. We have to come up with another symbol for momentum because, as you can see, we already represent mass with the letter M, so we represent momentum with the letter P. So your momentum is equal to your mass times your velocity. Large objects have more momentum and are harder to stop, okay, connected to inertia that we've talked about already. If the net force on an object is 0, then that velocity isn't going to change, which means as a result of that, the velocity doesn't change, then that means momentum doesn't change either. So the force is equal to mass times its change in velocity, which means that the force is also equal to the change in momentum. So your force that you're measuring will be equal to whatever the change in momentum for that object is. Anytime that objects collide, momentum is transferred from one object to the next object. And that's because of the law of conservation of momentum, which states that the total momentum for a group of objects is going to stay the same unless outside forces act on it. Okay, so you're not going to suddenly change the momentum of the group of objects. It's just going to be passed from object to object. So, for example, if you have a group of pool balls on a table and you hit them with the cue ball, the momentum doesn't change. It's just passed from the cue ball to all of the ones that it just collided with. Okay? Outside forces can act on it, and they can change the momentum of the whole group, like friction. So I have this Newton's cradle here. And you can see that when these collide, the momentum is transferred. But over time, they stop moving because that momentum is lost to friction from the strings that are attached to them. If we could remove friction, they would just perpetually keep moving in that motion forever. But we can't remove friction, so they are eventually going to lose their momentum and slow down. There are two types of collisions that we're going to talk about in class. Okay? The first is elastic collisions. This is when objects bounce off of each other after they collide. Okay, so the example of the pool balls there is one hits the other and it bounces off and continues on. There are also inelastic collisions. A good example of inelastic collisions when objects stick together is a football tackle. If you tackle somebody like you should, you will both stick together and go to the ground. One of them is not going to run off from the situation. Okay? In both of these cases, momentum is conserved. It's either transferred to the other object or the two objects then have the momentum. But it's always conserved. This is where our notes end and where we're going to pick up with the activity.